Numerical solutions also extend to taking the derivatives. Check out how to approximate differential calculus here in numerical solutions to CE problems. Let's take a look at the process in differential calculus. In its basics, rate of change is solved by differentiating a function. The derivative of y with respect to x is y prime, and the rest of the function has the derivative as 3x squared plus 5. In case we are looking for the rate of change when x is 1, all we needed to do is to plug 1 into x and get y prime value as 8. Again, y prime is the slope or the rate of change. But calculus starts with a given function, and in application, we have datasets and experimental values instead. Allow me to shed light to approximation, starting off with a dataset. Say the experiment yielded concrete strength in different durations. Taking days as the independent variable x, then concrete strength as the dependent variable y, graph the dataset, and connect the points. In case we are tasked to determine the rate of change or the development of the concrete strength on day 2, this simply means we take the tangent line on the second point on the curve. This can be determined when the graph is efficiently drawn with proper scaling. However, that would take more time. So analyze the situation more analytically. Rate of change is simply the slope, and we know that slope is the ratio of rise with run, or that is delta y upon delta x. Slope is labeled as f prime of x in calculus, and delta y can be taken as the difference of y coordinates over x1 minus x0, as explained in analytic geometry. At this point, we have gone away from differentiation, and slope is taken using points. The next problem is we need 2 points, one to make x0 y0 and another for x1 y1. Since we are interested with x of 2, this point is definitely where we focus on. But what can be the other point from the dataset with several points? A simplified picture is better in the analysis, so we take 3 points, A, B, and C. Say that we are looking for the slope at point B, and the tangent line we can draft as shown. The x-coordinate of point B is tagged as x sub I, and its y-coordinate is f of x sub I. Point C then has x-coordinate of xi plus 1, and the coordinates of point A are xi minus 1 and f of xi minus 1. Since we require 2 points, one being the given, assume another point, taking the one after B, that is point C. The slope is delta y over delta x, and from the illustration, delta y is the y-coordinate of C minus y-coordinate of B. Delta x is the x-coordinate of point C minus the x-coordinate of point B. Using the labels, we get f of xi plus 1 minus f of xi all upon xi plus 1 minus xi. Now take a look at the x values. Since they are independent variables, they are usually designed to have regular gaps, which is notated as h. Thus, the rate of change is then f prime of xi, which is equal to the difference of f of xi plus 1 and f of xi, all upon h. Again, f prime of xi is the rate of change as a specific point we are interested in. F of xi plus 1 is the y value of the succeeding point, in this case point C. F of xi is the y value of point B, and h is the x interval. This function is named 2-point forward, with point B as the given and point C, the succeeding point, as its helper. Another assumption is working with point A along with the required and given point B. The height distance of the 2 points is provided as f of xi minus f of xi minus 1. The x distance of the 2 points is also taken as xi minus xi minus 1. Just like how the slope is solved in the previous derivation, delta y over delta x is f prime of xi, which is then f of xi minus f of xi minus 1, all upon xi minus xi minus 1. Again, x intervals are regular and tagged as h, making f prime of xi less f of xi minus 1 all over h. F prime in the function is the rate of change at point xi, and f of xi is its y distance. F of xi minus 1 is the y distance of point A, and h is the x interval. Using points A and B, the function is named as 2 points. Then going back 1 point from that of concern makes the name 2-point backward. If points A and C can be used apart from B, it can also be assumed to use points A and C without point B. In this case, y distance is then f of xi plus 1 minus f of xi minus 1, and the x distance is xi plus 1 minus xi minus 1. Place these values into the rate of change function, taken as delta y over delta x, or f prime of xi. Again, from the x-axis, the values are regularly gapped as h, where in this case there are 2 jumps, or 2 h's, making the function f of xi plus 1 minus f of xi minus 1 all over twice of h. F prime is the required point's rate of change, and f of xi plus 1 is the y distance of point C. F of xi minus 1 is the y distance of point A, and h is also the x interval. Involving 2 points A and C and placing the required point at the middle, the function is named 2-point central. Just to clear out labels of each coordinate, let's have a curve of numerous points. Saying that we have points A, B, C, and D until we reach E, and we are concerned with the details for point B. This point will have an x-coordinate of xi, and the y-coordinate of f of xi. The one before point B, and that is point A, will carry an x-coordinate of xi minus 1, and a y-coordinate of f of xi minus 1. Then point C will have x-coordinate of xi plus 1, then y-coordinate of xi plus 1. In case there are more points, such as point D, its x distance is labeled as xi plus 2, with y as f of xi plus 2. And if there is another point E, its x-coordinate is now xi plus 3, and so on for the other points of the curve. There are a few more functions to use in approximating the first derivative, but we are not to derive the longer ones here anymore. The table shows 6 functions to serve for the rate of change, and they are derived using calculus. What we can do at this point is to determine a pattern to easily remember them. First, the name of the method states the number of terms or points involved. 3-point forward means there are 3 points starting from xi. Forward means the other 2 points are after xi. Thus, there are xi plus 1 and xi plus 2. Another pattern is in the operators used, and terms are separated by alternating signs. Observe a plus minus plus for 3-point backward, then a negative, positive, negative, positive for 4-point central. Since this part of approximation works with calculus applications, seldom would one hear about solving for the first derivative, but instead, the requirement will be termed differently. In mathematics, the first derivative is called rate of change, or tangency, and the second derivative is known as rate of curvature. Physics has got a more profound set of terms for the derivatives, from velocity for the first derivative, acceleration for the second, then also the other terms until the eighth derivative.